now we're live with Pleb Lyra and myself, Gary Kraus, and we are going to be programming some Bitcoin this evening, specifically going through Jimmy Song's book. We're pretty deep into the book already, even though we're not, we're looks like what 76 pages of 300 and some. So we're sort of deep. I think by chapter wise, where are we at chapter wise? Chapter 3? Yeah, we haven't quite hit chapter 4 yet. So chapter 3. But we've been doing a lot of fun stuff. At least fun
Yeah,
for
the
us.
holidays were upon us, so we had to take it easy for a while. But now, yeah, we have a lot of time to devote to it. We're gonna go deep this year.
Exactly. And you mentioned something before we were on the stream. You had mentioned something about you discovered something. Well, first of all, you realized I think on the last stream we were talking about this scalar multiplication, and we were like, oh man, like it's not in this book. Well, we just needed to like scroll down a few more pages, and then it talks
Yes.
about coding scalar multiplication. Um, so you'd pointed that out to us, so we just got we caught back up to where we were at in the book. And it sounds like you went a lot deeper and found some issues, or talk to me about that.
Yeah, it was. There is something with the implementation of the addition function on points. So in the answer keys for not even in the answers, but in the code that they offer on the Jupyter Notebook. Maybe if you load up the code, we could go through it together. So maybe open you have our project there. So let me show you where I landed in some issues. So when we're adding points one to the other,
Yeah.
yeah. So open up, yeah, chapter. First, open up chapter 2.
Let me clone this down.
Yes. Okay.
Because I'm pretty sure there's what you can just run this probably locally, right?
Mm-hmm.
Okay. Download. Cool. Virtual ENV. Okay, so we don't have that yet, but we'll get it really quickly. Okay, yes.
Or maybe, yeah, if you just open the files, because I don't think we'll be running it, anything.
Okay, that's fine. You said chapter 3.
Yeah, go on 2 first, and I want to show you the difference. So chapter 2 first.
Okay. And
Then open the code.ecc. Or, sorry, ecc.py.
we can do this. We'll just
Yeah,
open.
Yes.
That way we're looking at actual code. Not GitHub's okay for browsing some things, but it's not my favorite.
Mm-hmm.
Okay, so you said chapter 2.
Chapter 2, then ecc.py. Yeah, then we can have both open at the same time. So if you look at the point addition class,
This here.
or the point class, this is the field element. So
Okay.
scroll
Yep.
further down, and then for the
Point.
for the addition implementation, you have all these different. Oh, interesting. It's not implemented there fully.
Well, and that's because I think the exercises in chapter 2 were to write some of this code, right?
Mm-hmm. And then let's look at the same place for chapter 3. So point class add. So where I found an issue is on the if self X is different than other X, which is case 2.
Right.
Oh, interesting. Okay. Maybe that was me. Because yeah, so maybe it was my mistake. So I added first if self.x equals other.x and self.y equals other.y. And when 2 points got added, you know how when points are added inside a field element, it's just totally unpredictable where you're going to end up.
Right, right.
And there were 2 points that when you add 1 point to the same, it's actually the same y. It's like they're in the same height, just in different axes. When you add the same point to itself, it lands on the same y.
Mm-hmm.
And that's what was causing issues for me.
I mean, I think that might be possible.
Yeah, I can pull up let me find the addition that caused this.
When they had I remember they plotted it, once you use finite field arithmetic, you get like some weird effects here.
Totally, yeah.
And I mean, this looks like it's a pretty small sample size.
Mm-hmm.
Okay.
We could maybe run this addition to so I can show you which one it was. Just find the example.
Yeah.
That's the example, exercise 5, right? Chapter 3, exercise 5.
Chapter 3 exercise. Okay, yeah, that was one that you had messaged me about. I do remember that.
That's exactly the one that I was struggling for a couple hours today.
So let's see what it says. You find the group, right?
No, it's still just a. Oh yeah, it's the one to find the group. Correct. There it is.
Okay. So I mean, we can do. Let's do this. Let's.
Do this.
Yeah, let's try to do exercise 5. Because I was looking at this too, and this whole chapter. I read this chapter today, on sort of like the mathematical groups, and it might be good to understand more of how we get to a group, like the starting point, right? Because this is. Oh, yeah. So this is like a starting point or an origin point.
Yes, the origin point, the generator point.
Generator point, right?
Or just the generator. I think.
And then the order is the size of the group, right?
Mm-hmm.
Okay. So, yeah, let's we'll hijack another one of these tests.
Nice.
Or we'll just write a new test, just to, so we can run it. We'll just call it exercise 5 because I'm not creative this evening. So, all right, exercise 5. Let's copy this text out real quick. Maybe. Just put it in a comment. Okay. Generated by this. So, my first question is like, where do we plug in the origin point? Or it's like, yeah, where does the generation start, or their generation point? So, I mean, I guess first let's define the point that is like our generation point.
Mm-hmm.
I'm sure that will be relevant.
Because we'll be adding it to itself, yeah.
Right. This will be field element. Oh, let me get you a share link so you can so you can help me code this thing. Do not want to forget that. All right, we are copied. I will send it over in Discord.
Okay.
As soon as Discord starts up. Yeah, I've been going through. I've been doing a little bit of Go learning, like I said earlier, and Go has a nil character or a null, and that kind of upset me coming from Rust. It's like I know with Rust, I won't ever have a null issue unless I force it on myself. All right, the share link is out for your consumption. I'm gonna keep churning on this guy. Field element new. So our X is a 15. The prime is gonna be 223. And that's 86. 223. And this is 0, 223. And last but not least, the B, which is going to be 7 and 223. Okay. All right, so we've got that sort of. What is this? Oh, it's an optional. Whoops. Okay.
A and B are no, X and Y are optionals.
Right, yeah, because we added.
Because then they can be. That's when you can have them as null.
Right.
Cool.
Okay, so that worked. We have our generation point. So let's go back through we can go back through the book. And I mean, this is a pretty lengthy, there's a lot of like exercises and coding and stuff like that. But previous to this exercise, there's a lot of text. Talks about the scalar multiplication, which we implemented that last session, right? Or we talked about it at least, but we didn't handle the zero case. Right?
Yes.
So maybe we should do that. We'll get to it when the book calls it out. We already got ahead of ourselves. But it talks about scalar multiplication. It goes into it. It talks about there's not really a pattern to it. And then it talks about how this scalar multiplication gives us the asymmetry, which asymmetry is. Let's see, somebody is in the chat and they want to. Oh, no, thank you, chat person.
Yes.
Yeah, I do not want promotion. Anyway. So it talks about the asymmetry part of it. The asymmetric cryptography is what enables Bitcoin to do what it does, where you have that private key and that public key, right? Where you closely guard your secret and only expose your public keys. Yeah, and you can only solve it one direction.
And then once you're scalar multiplying a point, aka adding a point to itself over and over again, at some point you're gonna reach the identity point, which is the point at infinity.
Right.
And once you find this point at infinity, that's when you found your group, your cyclic group, or your finite cyclic group.
Right. Okay, that makes sense. And I do remember reading that. Okay. So basically we're taking this generation point and then we're applying scalar multiplication to it until we hit the identity point or the point at infinity, and then everything, every element that we encounter at that during that iteration, we put into our group, right?
Mm-hmm.
Okay.
Yes, those are the points in the group.
And it goes over sort of like the properties of these mathematical groups, like the identity, closure, invertibility, commutativity. Nailed it.
Which are very similar to finite fields properties.
Right. And it makes sense because we're using finite field math, like the core arithmetic, to get these mathematical groups are using the modulo arithmetic that finite fields use.
Yes.
It's crazy how all these math concepts kind of like build on each other. Like that was something that it's like, oh, you just use this special math and now you've got it.
And then when you're applying to the Bitcoin curve, you're using a number set that
right,
includes more numbers than the atoms in the universe.
Yeah, that
same basic concepts.
Yeah, that's this. How big is 2 to the 256 squared? That's pretty. The crazy thing I thought about that is this number. Where is it? This number fits in 32 bits. Like that was that was something that. Where was it? Maybe. All right, it might have been in here. I don't remember exactly where it was, but it was talking about like this number itself can be represented using, 32 bits, which is why Bitcoin is enabled to here. Amazingly, any number below 2 to 256 power can be stored in 32 bytes. That way we can store a private key, and that enables you. It's interesting that I could do 32 bytes, right? Because we've been using, what was it, U64s, so unsigned 64. So we have like double the amount of memory space that we would even need to store these things. Now, not memory like disk memory, but memory like in the stack.
That's great.
Yeah. So yeah, and just some comparisons. But all right, we're here to generate. So we need to essentially do this scalar multiplication until we find that infinity point.
Yes.
So I mean, I guess we should go back and address our scalar multiplication just to. Well, no, we can't. Go ahead.
In the implementation that we have there, it is just couple more lines, because instead of starting at the actual point, you start at infinity, which is 0.
Oh, for the multiplication, like it's yeah, that makes sense, and then add on to it.
Yeah, it just changes your starting point in a way.
But this is, I mean, we're finding we're not coding this to sort of work as multiplication. We're coding this as we want to find the order of the group. So let's create let's create a variable called order, which should be, we know now that it'll fit in 32 bits, right? So we can make it U32. And we'll have it 0 for now, right? Because currently there's just sort of 0. And let's see, what would be the next thing?
We would use a while loop.
Yeah.
We'll say while the result is different than infinity.
Yeah, so we can do while true right now, and we'll set like a break condition. Do you know that?
Cool.
You've done those before, right? Do you know what I mean by setting a break condition? Like there's a keyword called break.
Yeah, no, I'm just, I know that, but not exactly how to set the break condition. Oh,
Oh,
you say like
it's
if X break?
right.
Oh.
Yeah, so we have this order, right? And so every time we go through here, we're going to order plus plus. So we're going to increase the order by 1, right?
Mm-hmm.
And then we need to take, let's see. We need our the new point, or the sum. It's a sum, right? Let's use math terms. So the sum is going to be equal to generation. Oh, we kind of need to keep track of the sum outside of this loop as well.
Oh yeah.
So we'll do that as well. So we'll do sum equals, and this is, I mean, because we're starting at a point already, we'll just clone the generation point.
Cool.
Right. So the first iteration, this doesn't like that. Unexpected problem. Okay. Maybe this is the syntax. But sum is going to be changing, and sum is going to be plus equal to, which I don't think we can do with finite fields, because there's like another. This is a Rust thing, but Rust add assign, I think it was, and I think we looked at this last time, didn't we?
Oh yeah, we did add a sign. Yeah.
Yeah, this add assign trait we did not implement for our points, so we just have to do like manual plus sum, like this.
Okay.
And so okay, so we increase the order because we're on the first iteration through. We add the generation point to itself, essentially, or we keep adding the generation point to our running total here.
Mm-hmm.
And then, I mean, I think all we need to do is just an if statement. So if, sum dot x is none, and sum dot y is none, then we break.
Nice.
Right, and that should, what is this? Control val type of, to know infinite loops with loop. Oh. Okay, so it just says just use loop. Oh, that is way nicer.
As opposed to while true.
Right, yeah. It's just like, okay, we know what you're doing. Just loop forever. We loop until infinity. Like Galaxy Brain, you know what I mean? Like that's we're looping until infinity.
With the equations.
Yeah. Okay. Cool. And then once we have that, we should just be able to print out order. Doesn't like that. Oh,
where is it? Oh.
You got to get like a formatted string thing. Yeah, I think that's it, right? Like, does that sound? Is that?
Yeah, no,
that's super simple.
Really good.
All right, let's see. Let's see what this. 6 is 6 the answer?
As you taught me last week, we're off by 1. Yeah,
are we? Are we one? We're at 1 over, aren't we?
We're 1 under.
1 under.
It's supposed to be
because
7.
because we don't count the infinity point.
Yes, the infinite. Wait, do we?
No. So we would have to do this. This would solve it. The off by 1 error. Because what we do is
Mm.
if we get to infinity, which infinity is part of that group, right?
Mm.
Because it's part of the identity property, right? Yeah. Yeah, there's the 0 point or the point at infinity. So we need that as part of our mathematical group, as part of our set.
So like 6 is the number of elements we have in this set, and 7 is the
Infinity.
order. And infinity,
Right,
yes.
right. Yeah, and because the infinity is always part of every set
Mm-hmm.
or every group.
Oh, nice. Yeah, and you added the 1.
Right, now
Yeah,
we get
spot on.
7.
Nice.
Cool. So where did you get hung up on that one then?
It was. Let me just find where I want to add for point. Other is none. Other. So yeah, come to like line 60. Where equals now self equals other.
Line 60 in the
Where is
Rust?
self is not equal to other. Like if self y, if self x and other x are different. On line like 60, around line 60. That's the point.
You talking about this?
No, it's when you're adding the points and they're not the same, because we have all these checks to see if the point is the same, right? And then when the point is different. I'm looking for when the point is different.
So it would be here, because we check
Okay.
here if they're the same, and then we do this function, and then so it's two different ways of defining the slope, right? Is that what?
Yeah, yeah. I think it will be tricky to find it here, but there was a condition that I had that then the point addition wasn't landing in any of the conditions, and it was returning none. Because you have all these checks. Is the point like this? The point like that? The point like this?
Yeah.
And because of the way the results worked, it wasn't matching with any of the conditions, and then the addition was returning none. And
Okay.
it's not like it was returning infinity.
It's
It
just
was
returning
returning
none in
none.
gen. Oh, interesting.
Yeah. Not
I'm
not like point none none AB, right? It's
right.
just none. Yeah. So
Yeah, I mean, if
then I
you
figure out. Yeah.
do you have the numbers that you used for that? Do you remember?
Can you add a print to your test?
Oh yeah.
You see where it is. Yeah, add a print at each of the additions, and then you see where. I'll show you what I was talking about. So we see each of the points. Since it's only 6, it's easy to follow.
Oh, you're talking about in that test that we just did?
Exactly. Yeah, on the test that we just did,
Okay.
add a print at each step of the way. Like print the point.
Yep.
Little smirky face there.
Yeah.
With the question mark.
So let's see. All right, let's see this thing. Just make this full screen for now. So, all right, hold on. We can clean this up a little bit. It's got. Well, never mind.
Oh yeah, so even so check this out. The first 2 points. So the first point,
Mm-hmm.
15 and 86, right? X and Y.
Yeah.
And then the second point, 139, but also 86. So that's what tricked me. My check was expecting Y to be different as well. And in this case, you're adding points and they're just moving horizontally in the same height.
Huh. Yeah. No, that makes sense.
Yeah, and then that's why the addition wasn't working. So I removed the check for the y to also be different at the same time, and then the addition worked fine.
Gotcha. Okay.
That's interesting. Yeah, they go like from 86 to 137 and back.
Yeah, I was just looking at that in like these numbers, it kind of like circles back to itself as well.
Yeah.
Like 1586, 137, and 139 and 69 are like the only numbers in this.
And they're just like, yeah, interchanging.
Yeah. It's different permutations of it or whatever.
Yeah, such a small set.
Math is weird, man. All right, let's
Let me ask you something then. You might have done this, but I was trying today to plot the numbers. It doesn't have to be visually on a graphic. I just wanted to be able to find more points in the curve and find a way to program that. I think you did that, right?
Yeah, I did that.
For any x, like just find a bunch of numbers in the curve, you know.
Yeah, so this is how I did that. I took the order basically, and I iterated through each thing and sort of printed it all out, and I got a list of it.
Nice.
But you want to point all those on a graph?
Doesn't have to be that. I just wanted to find points to do some operations with them and tests.
Well, we have this.
Oh, you did. Okay. Nice.
Yeah, we have all these points. So I wonder, there's got to be like a I don't know, plot points on graph. That would be interesting to generate some.
And these are inside, like the finite field.
Yeah, this is the
finite fields. Yeah, everything.
Yeah, this is there we go. That's cool.
Okay.
That's so cool. Yeah, I just copied it into here and it just plotted it all. And so this is with the prime at 191. And so I just cycled through 1 through 191 for both x and y, and found all these points on the curve. Yeah. It's the cool part is like there's like a reflection over this midpoint, and it looks cool. Like if you look at it like turn your head to the side, sort of thing. Here, hold on. We do this. Like I feel like there's some cool like trippy art in there.
Yeah.
Some way. How do I rotate this thing?
Probably see many objects there. Yeah. Oh, cool. That's amazing. So I copied your block and we'll translate it to Python.
Okay. Yeah. Please do. There's really no way to rotate this thing. That's kind of upsetting.
Oh no, that's undo and redo. Never mind. That looks like it. Yeah.
Rotate right. There we go. All right, well, we lost it. Anyway, it'd be fun to connect the dots and try to make some gnarly, like, thing, I guess.
Nice.
Yeah. Like, I should print this out and have my kids, like, connect the dots with it.
See what they can come up with.
All right.
Nice. Okay. Thank you for that. Yeah.
Yeah, no worries, man. Yeah, you should. I mean, that should translate pretty easily to Python. So
Mm-hmm. And the numbers, the results are all integers, right? There's no floating point, no anything weird
yeah,
about it.
everything's unsigned integers. There's
Mm-hmm.
no, not yet. There's no floating point yet, to my knowledge.
No, yeah. Nice. Okay. Thank you. That's awesome that you can just dump a whole list of points into Desmos
Yeah,
and they'll plot it.
yeah, we should monkey around with that again once we get some more points in the future.
Mm-hmm. Okay. Amazing.
Okay, so coding scalar multiplication, which we didn't have. I don't know if we named it good. I mean, we named it like multiply by. I mean, I guess that works. We could probably give it a better name, but we're not going to right now. So this is that one that they just. Okay, so we can write a test. We can write a test for this scalar multiplication, which I think we already did. Yes, we did.
250, row 256, yeah.
But we can just write another test based on the example in the book here, right?
Mm-hmm.
So let's copy this point. And expected. And these become nuns.
So the expectation is that it would land in the infinity point.
Right.
And this would be 15 and 86.
Yep. Yes, thank you, sir.
Point.
Yeah, we'll assert equals.
Multiply by 7.
Yeah, points dot multiply by 7. And then that should work. So we can run the test real quick. Boom. All right, so that works. So what were we missing then in our...
In this implementation, if you need to multiply by 800 million,
Right.
that would be an issue. But also, if you want to multiply by 0.
Yeah. Yeah, that's true. So let's... And it goes... Yeah, we'll just skip to the one where it talks... Where we're programming like the large coefficient sort of equation. Which uses binary expansion. So to keep it consistent with the book, we'll go ahead and update this to be coefficient, because I think that makes sense. Why does it assign it to itself here? All right, let's see. Current self. Oh, it's because they're modifying it. So, okay. Yeah, we'll just get rid of all of this for now. Let coef, and we need it to be mutable.
If you don't add the mutable, then it's a constant.
It's not that it's constant. It is immutable, meaning you cannot change it. So in this, like line 5, or not line 5, like on the left here, like these lines, like this little 3
Mm.
and 5. Um, well, not that necessarily, but this is a bitwise change, right? So this is shifting bits of the coefficient, and so you're mutating, you're changing the coefficient, and then current, you're modifying it, right? Result, you're modifying it. So they need to be mutable, meaning they can be changed.
Mm-hmm.
If they are not mutable, then you can't. Rust will yell at you and tell you to make them mutable or don't change them.
And how would that be different to a constant? Is a
So
constant a thing?
yeah, no, constants are a thing. It has to do with how the compiler handles it. So the Rust compiler wants to prevent you from sort of like referencing things that have changed without knowledge, or referencing like a null reference, right? Because if it changes to something that's not there, or to a null, like the reference is just gone, that's where like some of these other languages, and again, this is, I never done C++, I've never done C. Rust is my first sort of systems language, so this is my understanding of it. So please don't trust on this one, like go verify for sure. But, you know, it is checking at compile time, and it's ensuring that it's compiling in such a way that you're avoiding those sort of references to something that doesn't exist. So if you say that, you know, hey, this is mutable, then the compiler does some behind the scenes magic to make sure that it safely changes, and the rest of the code is aware that it could possibly change, and it will not necessarily let you write code where the change is bad, if that makes sense.
Okay. That makes sense. Thank you.
Yeah, but if you make it immutable, it just doesn't change, period, ever. And so until it goes out of scope, and then it just goes away. And there's this whole thing actually with like Rust lifetimes, which is something that I've yet to fully grok and go over. Like you can give something, because the way that like Rust manages its memory and stuff, you can essentially assign a lifetime, and the compiler will do this sort of like implicitly with the way that the code's written, because there's certain patterns that imply certain lifetimes. But they took some of those like reoccurring patterns out and just made like the compiler smarter to like know that like, hey, every time you see this sort of pattern, it means that the lifetime of this variable is for this set duration, or this in this set scope, not duration. Duration implies time, but in this set scope of code. But you can manually put like lifetimes on a variable to ensure that that variable does not fall out of scope and like disappear, sort of thing. But yeah,
this is all like dealing with extracting as much performance as computationally possible.
Well, no, it's not necessarily performance, right? So because like we're cloning these things like that, there's probably a way to do it without cloning it, but we're not writing this right now for performance. So we're just going to clone these things. That way we don't have to, well, we can try it without cloning actually. I think it just clones it under the covers anyway, because it's all on the stack, if I'm not mistaken. Unless you make it like a reference to it, but then there's some weird implications for like throwing around references, and mutable references are handled like there's a mutable reference that you can use. But it all has to do with memory safety. It's not necessarily performance, because you can write some really like unoptimized code if you're not careful, I guess. But what you are not going to write is like, if it compiles in Rust, it's very likely not going to have like a runtime error, because unless you code it in there, right? Because of the way that the checks, maybe runtime error is not the right thing to say, but like if it compiles, it's probably going to run. Is sort of like one of the Rustisms. It's not always a guarantee, but it's more of a guarantee than something else. Like something else might crash with like a null pointer exception, which is like the $1 billion mistake. And there's some statistic that the Rust community likes to throw around where it talks about how I think it's like 70% of security vulnerabilities are somehow associated to like memory management. So yeah, like because if you some of the ways that like hackers or people that are trying to like break stuff is they find where limit is or where like a memory vulnerability is, and then you do like a buffer overflow where you push so much data into there that it can't, the system can't handle it, and you start accessing memory that is not where you're not supposed to. And that's a very simplified way of explaining that, but anyway, we can.
Because of that, it might happen that some Bitcoiners with a lot of Bitcoins stored in a server might end up losing their coins. Some famous Bitcoiners.
I've heard of that. I heard about that. Yeah, I don't know
how that happened, right? It's still an incognito.
Yeah, I don't know how that. I mean, anything that's online, right? Like that's why you use a cold wallet. That's why you use a cold card and you air gap it, and it never touches the internet. And the worst thing that can happen is you leak your XPub, and then everybody can see all your transactions.
But they don't. Yeah, they can take.
But they can't move your coins, right? Yeah. It's just, yeah, I don't know. Cold card.
We'll know what happened there. Yeah, I'm very curious to
learn
more about what really happened there.
I've been off of Bitcoin Twitter, so I don't,
That's right.
Yeah, I don't have. I heard the story just through like no BS bulk, no bullshit Bitcoin, and some other just like channels, but Twitter is off my phone, so I'm not. I have been on Nostr a little bit though, but only at my desk. I actually. Anyway, I don't want to go too far on a tangent. That's not related to programming Bitcoin and Rust, but needless to say, I deleted the Damus app, and then the creator of the Damus app commented on that with an emoji of like an expressionless face. But it was good. It's a good delete. I've been way more present with my family because I'm not doom scrolling on Twitter all the time.
That's a wise decision.
Yeah. I just doom scroll on my laptop when I'm sitting in front of it.
That's already,
anyway, we're writing.
Gained an extra hour a day, probably.
Probably, yeah. But we're writing scalar multiplication for finite fields for elliptic curve cryptography. Something that never in a million years would I ever think that I'd be saying out loud.
Monday night.
On a Monday, that's right. So we have one other variable here that they look like they're mutating, which is this result, which for the scalar multiplication, as you had mentioned previously, we're starting at 0, which I thought we defined a constant 0, didn't we? Did we do that?
I don't remember.
Maybe not. We defined a prime that was a constant. We should define like a constant that's or a function that gives us a 0, like infinity or something like that. So let's just do that so we don't ever have to write that code again.
So every time you call that function, it just returns a point at infinity.
Right. I guess we do need to give it the A and the B. This is none. It's none. This is A.
Don't your A and B need to be field elements?
I don't know because I don't want to type all that out, right? So I'm trying to save on like typing things.
Then you're gonna make them field elements in there. Okay.
Right. Oh, and I guess we need the prime too. Colon, and A, and prime. Yeah, cool. No, we don't want that at the end of it.
Okay.
Just because we're defining a struct here. So we're defining the point struct, and then we don't put it at the end here because that's just the return value. And so now we can do... Oh, wait, we were up at multiply by. I'm all over the place. Oh, it's right, literally right above it. So, okay. I think we can just... Nope. So what is our A and B? So it would be self.A, self.B, and self.prime.
So I was learning this today. Would infinity point be a subclass? No, right. Infinity point is a function.
Yes, yeah, it's a function. Sorry. I had to think about that for a second. Yeah, so fn is defined as a function. It's a public function. So it's available to which it might, I don't think we need it to actually be a public function. We could probably just do this. I'm not mistaken. No, maybe not. Oh, self. That makes sense. Yeah, public makes it available outside of this module. And then we do need this. Oh, all right, whatever. It reformatted that. Okay, so we have these three mutable variables. While coefficient. So what does this do? What is it? While coefficient. We are looking at whether the rightmost bit is a 1. If it is, we add the value of the current bit. So we'll have to look up this operator. And this is going to be interesting because I'm assuming in Python when you're bit shifting. Okay, so we need to look up the Rust bit shifting operator because this is kind of the crux of this is, while coefficient, which I'm assuming once you bit shift beyond the last bit, it becomes a none value, and so it breaks that loop. Does that make sense?
No, but keep going.
So in Python, right? So what would break this while loop?
When coefficient becomes
none.
Okay.
Right? So when coefficient...
when it shifts the last bit. Okay.
Right. Yeah. So once it shifts that last bit, it becomes none. It goes to evaluate that and it says, oh, nope, we're done here. And then it returns the result, right? So we need to look up how to do Rust bit shifting. Because I'm assuming that there's a function to bit shift by a value, right? In this case, 1, and that's probably going to give us an option or Yeah, an option, not a result, an option. And then we can trigger our condition to break the loop off of that option. If that makes sense.
Mm-hmm.
So, yeah, let's look up Rust. Actually, let's go to ChatGPT 3 and ask that question. Because this ChatGPT 3 is like, I enjoy pair programming with ChatGPT 3. Not more than I enjoy pair programming with Pleblira, but, you know.
Thank you. Machines will not take over. Not today.
It's kind of funny that there's this, like, I'm not a robot to get you access to the robot.
Very interesting. Robot doesn't want to interact with, right? It's on.
Right. Why did that not log me in? Uh-oh. Well, we don't want the robots interacting with each other.
That would cause trouble.
All right. What's it called? Bit shifting? Yo, that's cool. So I guess you can't. Excuse me. Ah, I knew it. So the SH1L and SHR. Because we're shifting to the right. Yep.
That's the right.
So I'm curious. So I wonder if it would overflow. Like, does it overflow? So how, when you shift an integer, dude, I'm telling you, see, this is amazing. I love, this is like so incredible.
Scary.
Right?
But incredible.
Yeah. So the checked shift right is I think what we need. And it probably is in here. Well, we'll search for it. Yeah, check shift right gives you an option of it. So this is the function that we want for our excuse me, for the math. So that's cool. So we know that exists now. So we can set up our loop. So this is what, while coefficient is So okay. Yep. And then we need to set up our coefficient to be an option then. So while it is sum, we're going to do a thing. And go back to our programming Bitcoin. And we can check out, okay, so what is this AND operator in Python? Do you know what that is?
I was just looking this up, so I'll send you a link on Discord that's describing these operators.
Okay.
They're called bitwise operators, but it's kind of, scroll down a little to the bitwise operators. There you go. I don't understand that. It's off my pay grade.
Sets each bit to 1 if both bits are 1.
How that applies to that code in the book, that's what I don't know.
If coefficient here, let's see this. This is amazing. The code you provide is checking if the least significant bit of the binary representation of the variable is set to 1. Okay.
Least significant?
The one to the far right.
Okay.
Right? Because that's the ones place, right? The least significant.
Yeah, like the smallest, basically.
Right.
Okay.
This least significant bit is the rightmost bit in a binary number and it has the least value.
Mm-hmm.
When you use it to compare a bit with 1, it checks whether the bit is set. Interesting. So this line of code is checking whether the rightmost bit is 1. If it is, the code inside of the if statement will execute. Okay.
Oh, that's a different way of checking odd or even without using modulo too.
Listen, we're gonna blow through this book so fast because we just have ChatGPT 3, and it's like, hey, how do I do this in Rust? We just copy the whole code and say, convert this to Rust. Oh my God, we should do that with all the code that we've done already.
Oh yeah.
Anyway, sorry. Yeah, I don't want to make this a ChatGPT 3 stream, but it might be.
So you have there 1 equals 1.
Okay. To check if a specific bit is set by using a binary number with only that bit set. Oh, that's interesting.
With a mask.
So if you use a number, so like 16, basically any exponential of 2. Mm-hmm. So 1, 2, 4, 6, or 1, 2, 4, 8, 16, 32, 64, 128, blah, 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 on and on.
Interesting that he's saying... Oh, no, okay, never mind. Yeah.
But it tells you if that bit is set for that number. So, like, let's think of another... so I think this would also evaluate to true if the right-hand side was a...
11, which is like 1, 0, 1, 1.
Yeah. Yeah. No, is that 11? Yes. Yeah, 11.
Right.
Yeah. Huh.
Oh, interesting.
Oh, you can check odd or even with that. Yeah, that makes sense.
Uh, bit Bitwise. That's a Bitcoin company
This
name
is
there.
this is amazing. Yeah. As a self-taught developer, if I had ChatGPT 3 when I was learning to code, oh, anyway.
I need to start getting into it.
You should, man. And as you're doing these problems, just type like you saw how easy it
Yeah.
is. I just type in like, what is this?
Before they start charging,
Yeah.
$350 a month or so.
Is that where? Are you just pulling that number out of nowhere?
Yeah.
Okay.
I saw someone saying they would charge like $50 a month.
It might be worth it.
Right? Yeah, the amount of value we got from these two queries already.
Well, and just
It's
throughout my
very
day, like I've just been using it all day.
exactly. Mm.
So interesting. Anyway, so we can basically just copy the code, is what it says.
Yeah, very similar.
Except we need to unwrap it.
So So you're checking if the least significant bit in coefficient in coef is active.
Yep.
If it is, then you add the current to the result. Then you add 1 point.
Yeah, you add 1 point. And if it's not, you're gonna skip that point and you're gonna double current itself. Well, you're gonna double current anyway as you keep
And
going.
every time it passes through, yeah.
Mm-hmm. And then we're gonna shift this. And this is where we do the coef is now gonna be equal to coef dot
Checked.
Unwrapped, and it was checked.
Checked underscore shift right.
Shift right, yeah. And it'd be 1. And then that should work.
Nice.
And then result. It's the last thing we want to return. So that should work. Yeah, camera went out of focus. You're like super.
Hello. Yeah, I'm here. Whoa.
Put your thumb completely over it.
Oh, like, yeah.
Yeah, and then boom. Nope.
Maybe because I'm wearing black or something like that. Can't see me.
Yeah, I don't know. I don't know what's going on with that.
Oh. I can also turn it off. Maybe that'll help.
Have you turned it off and back on again, sir?
Yeah, we have it.
Heyo.
Like magic.
Well, so let's see if our existing test works, right? Because we had tests written.
Yeah.
The scalar multiple test. Compiling and building. I have a cat. My cat's destroying something behind me. I'm sure it's not expensive or anything.
Even though we know they aim for the more expensive stuff.
Yes, they do.
That's what they do.
What is going on? That test was taking a long time. Try it again.
Oh, is it still running?
Yeah, it's taking a while to build. Which I don't know why it would take longer to build than before.
So you mean it's not even running yet? It's still building, or?
That's what it says. It says
Yeah.
building. Yeah, it says building down here in the little indicator.
Mm.
Oops. So cargo build. Okay, so that built. We just do a cargo test. We can run all the tests.
Isn't it like in a crazy loop?
Yeah, maybe. Yeah, we might have programmed an infinite loop. That's a good point. Let's go. Okay, so yeah, we probably programmed an infinite loop. That's fun, I guess. And let's go back to this checked. All right, let's go back to this real quick and just
Check shifts right.
yeah, that should. You know what? Let's do something. Let's loop, and we're gonna match on coefficient, and so we'll have some. And this is a thing that we do if it's and then if it's none,
Okay.
we'll break. We don't need these unwraps anymore. Oh, so what's going on here? Expected a U64. Oh, okay. That's because this is... All right, we can... That works. We just had two variables named coef or whatever.
Mm-hmm.
So I didn't like that. Okay, so let's try that. Let's see if that will loop forever. What was it called? Scalar. Uh-oh.
Maybe add a print statement or something to
Yeah.
cover it.
Yeah, that's a good call.
That's what I do. I don't know if that's legit to do, but I have a bunch of print statements just to see where I am in the code when it's running.
Oh yeah, print. It's called print.
But
Well, there's that methodology. So it's called print line debugging, right? Where you're just
line debug.
you're printing stuff out. Now there's an arguably better way of doing that, and it's using the debugger. And so if we set this breakpoint here, let's save the file, and then we can do this. Let me split down. And we'll just keep this here near the test so we can run this, debug this quickly. Maybe. Uh-oh. Okay. So what are we missing here for debugging? I think we're missing there's some debugger extension that I think we're missing, and that's why it's not working. So we don't have that. Reload, sure. Yeah, we'll reload that real quick. I think it's like the LLVM something or another. This is where
it runs line by line. That's what it does.
Yeah, let's hold on. Let me see if this is the right. No. Rust VS Code debugger. So let's see if we can figure this one out. I know the icon for it. I cannot remember the name of it. Is what I'm coming up against. LLDB. I think that's what it is. Okay, C extensions. That's what we're missing. Now, will we have that then? Okay. Oh, okay. So add configuration. And it's telling us to add C++ Windows, which we don't have. So if we're missing, we're probably missing some of these underlying features. All right, well, I will address this another time. I think we're missing some of the underlying tooling to debug this, but it is a really nice experience. And yeah, we'll just print line debug instead, because nobody wants to watch us download a bunch of stuff.
Print line debugging. Okay, that's my jam.
Yeah.
I would like to get into some real debugging in the future.
So print line. So let's see. What do we want to know? We want to know what coif is.
Mm-hmm.
We also want to know probably what the sum is. Or no, we don't have sum in here. We have result. Sorry. Current. We should probably check current. All right, and then we'll run it. Oh boy.
You just loop infinitely.
Yeah. I wonder if that's... is that by design? All right, maybe we don't need... All right, let's look at this. It's kind of hard to read. All right, I'm going to do something real quick. I want to implement a better formatting for point for when we print that out. So the same way I think we did it for field element.
Yeah, it is hard to see what's going on.
Right. So this, but for point. And I kind of want to make this so it would be, we'll do a new line, X colon, new line, Y colon, new line, A colon, new line, B colon. That way it's just prettier, ideally.
Mm-hmm.
This would be self dot X, self dot Y, self dot A, self dot B. Another thing we'll do is we'll indent these, so we'll put tabs after the new lines.
Neat.
And we can do this. So tab, tab, tab. Do tab here. We'll do one last new line and another closing bracket. So that should give us a prettier print when we run these tests. So let's run it and see what happens. Oh, okay. Yep, we forgot to declare the crate. At the top here. Expected. Oh, okay. Yeah, we tried to pass it a character it didn't like. I think we can escape those.
Oh, I see what you want to like show it as a...
Right.
Yeah. Okay. Yes.
Oh, it doesn't like those. Oh, it's escaped with a double curly brace. Like that. What is going on here? Oh, okay, yeah, we forgot we gotta do this. The debug version of it. Cool. Now let's try it. Cancel out of this for a second. So the current still didn't print very nicely. Whatever. Oh, you know why it didn't? Okay. It didn't print nicely because we didn't tell it to. Oh, yeah, we did. Never mind. Coefficient is sum 0.
Ah, sure. Okay, so that's, even though it's shifting the bit, it doesn't become none. It's still like sum 0, but it's never becoming none.
Yeah.
This is what's happening. Could you do
It should
like
be
if?
6 at first, though, right?
Mm-hmm.
All right, so let's instead of looping here, let's comment the loop out just real quick. We'll put a no op in here. I'm curious what it prints out on the first run.
Mm-hmm.
And this is where a debugger. So a debugger, you actually pause the code execution in the middle of it, and you can inspect the variables at that moment in time. And then you just click continue, or you can step through the various
Mm-hmm.
you can step through. How do you explain it? You can step through the different logical flow of the code. And it's just a lot more powerful than print line debugging. Okay, so the coefficient is sum 3. Okay, so that's after we.
It was the first run.
Well, it's after we shifted it once. Okay, so all right. I think we just made a mistake in thinking. So this. Returning none if the right-hand side is larger than or equal to the number of bits in self. Ah, okay. All right. Okay. I see what it is. It's this checked. All right, so this checked version, it's not that it's going to prevent us from going beyond 0. It's just going to it's going to prevent us from shifting more than we have bits available. So for instance, the way we can get to none with this is if we tried to shift by 12. Right? So if we run this again, and that makes sense now that this is all clicking now. If we run this now, it's still 0. What? Read that again. Returning none if the right-hand side or the number passed in is larger than or equal to the number of bits in self. Oh, so would it have to be this then? Are we shifting? Try to shift by 65 because it's 64 bits. Okay.
Hmm.
Okay.
Yeah.
Yeah, because it's a U6, it's an unsigned 64, so there's 64 bits is the size of X. And so it won't let it only returns none if we're shifting that. So the real check, it should be if it's 0 or not.
If you just use the shift right as opposed to checked shift right.
Right. Yeah, I think that'll work. We way overcomplicated that, I think.
It was interesting regardless.
Could be wrong. And we don't need to match. So
Go back to the wow coef.
right, yeah, we'll go back to how it is in the book. Well, that's just this. Oops. And this is not X. This is coef. And coef.
Okay. You're gonna keep the loop and then break out of it.
Yeah.
Okay.
Okay, so this is still true. And then that's correct. And then this is just... Oh, I think we can do this even. Let's see. Yep. So it's almost exactly. And while it does not equal 0.
Oh.
Right? Maybe we'll have an off by 1.
Yeah. Yeah.
Let's try it. It passed instantly. It instantly executed and passed. Okay, so we did it. We created an infinite loop. Yay! We learned a lot about bit shifting in Rust.
Bitwise operators.
Yeah, and we way overthought it.
Yeah, I wonder why, like the example in the book isn't just while coef different than 0, you know what I mean?
Yeah, I mean, I guess like, so maybe that has to, okay, so and maybe I just misunderstood the Python, the Pythonisms or the Pythonish way where, while coef, so when you think about Boolean logic, right, like true, false, what is true? 1. What is false? 0. So if you do a while coef, if coef ends up being 0, I'm guessing that Python just evaluates that to be false and then doesn't run it. I mean, that would make sense.
Yeah.
But now we can do super big numbers.
Yeah, that's the fun part.
Now we can define some more elliptic. We can define the curve for Bitcoin. But as exciting as that may be, I think we should get to that another night.
Mm-hmm. Yeah, I'm gonna look into why we're not doing ycoef different than 0 and just ycoef. But yeah, as you said, maybe once it's 0, it evaluates to false.
That would be my guess.
Mm-hmm.
But I would just say take the code and put it into our favorite coding partner here. And
to get into it.
Yeah, and I think it would probably give you a really thought out answer. Anything else you want to ask the magical 8-ball before we sign out tonight?
Is there a way to ask what we were just talking about? All right. Okay. Yeah, let's do that.
It's thinking a lot.
Wow. Okay. Okay.
That's funny. Okay, all right. There we go. Okay, all this FUD. Okay.
Not financial advice.
What a bear. That's funny.
Yeah, there you go. Yeah. Don't sue the AI for your bad financial decisions.
That's funny. Wow, it's kind of getting defensive here.
Yeah. You tell
ChatGPT.
it to not conflate Bitcoin with other cryptocurrencies. Let's teach it. Let's see if it's still defensive.
We're fading. We're fading off topic, but I love it.
There you go. There's like
More
a
FUD, dude. It's just
disclaimer.
constant FUD.
Yeah.
Constant FUD.
They probably programmed this disclaimer for, real estate, stocks, crypto.
Right.
Yeah, crypto. Bitcoin.
Well, pleb lira.
It sucks that the crypto word got hijacked by scammers. Yeah,
It
that's how it
is
is.
what it is. Apparently, Bitcoin's price is doing something. I don't know. I've been off Twitter.
Yeah, I hadn't been checking much, but yeah, now that starts pumping, I'm like checking. No, man, it's fun.
Yeah,
Going up.
we'll check it. We'll check, and then we'll end the stream. We'll check. What's the good one to check? Bitfinex.
Well, I do crypto watch. So it's cryptowa.ch.
Ooh.
It's a nice interface.
Yeah, we pumped.
Yeah.
We're above 21K.
Yeah, we
Wow.
absorbed all that FTX bullshit and more.
Well, there we go. The bull market has begun.
I think so too. Tell that to ChatGPT.
Right. I hope it tanks down to like 5K a coin. That'd be
Buy some more, right?
yes.
Nice.
Sell a kidney. All right, pleb lira. We're gonna end the stream here. Any last words or closing thoughts?
I'm all set for today.
Awesome. Well, stay humble and stack sats, everybody. Thanks for tuning into Programming Bitcoin in Rust.